Bismillahirrahmanirrahim. Assalamu alaikum. I'm Dr. Shahid Latif, Associate Professor at Department of Computer Science, Sarhad University, Peshawar. Today we will start lecture number 3 of our course Electronics 1. The course code for Electronics 1 is ELC216. This course is offered for various programs including BS Computer Science, BS Software Engineering, BS Telecommunication, and BS Electronics. Remember that Electronics 1 course is a 2-1 credit hour course, means that we have to cover at least 2 hour theory classes, while 1 credit hour or 3 contact hours of our lab work. As we discussed that this is lecture number 3 of our Electronics 1 course, the major topic discussed or the major topic which we will discuss in this lecture is classification of matter based on their conductivity. Before starting our new lecture, let's have a look on the previous lectures, lecture 1 and 2. As you know that in lecture number 1, we discussed the prerequisite courses required for Electronics 1 course. And you know that the prerequisite course for Electronics 1 include AC circuit analysis and DC circuit analysis. In AC and DC circuit analysis courses, we discussed some important topics. For example, voltage, the current, power, and most importantly, Ohm's law. We'd also discuss that in case of multiple resistive circuit, how we will identify that the resistances are in series, resistances are in parallel, and how we will solve the combined series parallel circuit of resistances. We learned that what is KVL and KCL. KVL and KCL are two Kirchhoff's laws, abbreviated as Kirchhoff voltage law and Kirchhoff current law. Then we discuss voltage divider rule and current divider rule. We also discuss that there are several important network theorems which are required to have sufficient knowledge before starting our Electronics 1 course. These network theorems include the superposition theorem, maximum power transfer theorem, Thevenin theorems, Norton theorems, and some other network analysis theorem. We also learned that sufficient knowledge about capacitors, their types, capacitances in series and parallel. Similarly, sufficient knowledge of inductors, their types, their series and parallel circuits is also mandatory for this course. After discussing the prerequisite in lecture number 1, we define the term electronics in two distinct ways, the formal and informal way. After defining the term electronics, we learn that what are the major differences between electrical and electronics technologies. In lecture number 2, we learn that what is atom and what is the atomic structure of an atom. We also learn the Bohr model, the atomic number of any element, the electrons, their respective orbits, and group of orbits termed as shells. Then we learn valence electron and finally the ionization process. Today we will start our lecture by discussing the insulators, conductors, and semiconductors. Means the three different types of matters based on conductivity. In this section of our lecture, we will learn an example of a carbon atom. We will discuss the nucleus, the electrons, their orbits, and even core of the carbon atom. Then we will learn how insulators, conductors, and semiconductors differ. In second part of today's lecture, we will learn the energy bands. What is meant by valence band and conduction band, and what is the basic difference between VB and CB, means valence band and conduction band. We will also learn the energy gap or band gap. We will discuss the energy level diagrams for all the three types of matters, that is insulators, conductors, and semiconductors. After discussing the energy level diagrams, we will compare two atoms, one from semiconductor and one from conductors. After comparing semiconductor atom with conductor atom, we will compare the two most popular semiconductor atoms, that is silicon atom and germanium atom. We will finish our lecture by discussing the covalent bonds and the silicon crystal. Recommended books for this course and even this lecture is Electronic Devices, authored by Thomas L. Flight. We are using 9th edition of this book. If you have latest edition, it is also acceptable. Remember that Electronic Devices is available in two versions, that is conventional current version and electron flow version. Major contents of our course is from Electronic Devices conventional current version. So starting our lecture with classification of matter. We know that all materials are made up of atoms. These atoms contribute to the electrical properties of a material. Means that the atoms of every element will contribute in determining the electrical properties of that material, including its ability to conduct electrical current. Means that we will also learn from these atoms that whether this material will conduct or will not conduct. To discuss the electrical properties of an atom, it can be represented by the valence shell and a core. In previous lectures, we learned that valence shell is the outermost shell of any atom, while the core is everything including the inner shells and the nucleus, means everything except the valence shell is known as a core. These valence shell and a core concept is illustrated in figure 1.6 on the next slide for a carbon atom. Notice that the carbon atom has 4 electrons in the valence shell. As we know that carbon atom has atomic number of 6, so in its first shell there will be 2 electrons, while in its valence shell or the second shell there will be 4 electrons. 2 electrons are in the inner shell, so the nucleus of carbon atom will consist of 6 protons and 6 neutrons. Here the plus 6 indicate that the positive charge of the 6 protons in a nucleus. The core has a net charge of plus 4 because plus 6 for the nucleus while minus 2 for the 2 inner electrons. So collectively the core has a net charge of plus 4. Here you can see that a carbon atom is considered with atomic number 6. So you can see that in nucleus there are 6 protons while 6 neutrons. The gray color shaded area is termed as a core. In this area we have 6 protons while 2 electrons, so collectively the charge is plus 4 on the core, while there are 4 electrons in the second shell, which is also a valence shell for carbon atom. Now, what is insulator? Insulator is a material that does not conduct electrical current under the normal conditions. Remember that most of the good insulators are compounds rather than single element. And these compounds materials are having very high resistivities. Here the valence electrons are tightly bound to the atoms because the valence shell in insulator material are almost filled, so the valence electrons are very tightly bound to the atoms. Thus, we have very few free electrons in an insulator during or under the normal conditions. Some examples of insulators include rubber, plastic, glass, mica, and quartz material. On the other hand, a material that easily conducts electrical current are known as conductors. Most of the metals are good conductors. Most of the metals are good conductors. Best conductors are normally single element material such as copper, silver, gold, aluminium, etc. etc. Conductors are normally characterized by atoms with only one valence electron in their valence shell. You can see that here we have an example of a copper with atomic number of plus 29. So the distribution of electrons will be such that in first shell there are 2 electrons, in second shell there are 8 electrons, while in third shell there are 18 electrons. So collectively in first three shells there are 28 electrons. Only one electron is present in their valence shell. This single electron or valence electron is very loosely bound to the atom, and it will become free electrons even on or under the normal conditions. The third category of material based on their conductivity is semiconductors. Semiconductors are those materials which have some properties from conductors and some properties from insulators. Or we can say that semiconductor is a material that sits between conductors and insulators in its ability to conduct electrical current. Semiconductors in pure state, which is termed as intrinsic semiconductors, are neither a good conductors nor a good insulators. Single element semiconductors include carbon, silicon, germanium, etc. etc. These semiconductors material are characterized by atoms with 4 valence electrons, or we can say that half-filled valence shell. Semiconductor materials are also available in compound form. So the compound semiconductors include gallium arsenide, indium phosphide, gallium nitride, silicon carbide, etc. etc. Remember that silicon is the most commonly used semiconductor material, and you will see that throughout our course we will use silicon as a semiconductor material. As an exercise, you have to draw the atomic structure of some atoms or materials. To know the atomic numbers of these materials, you may use the periodic table. First, you have to draw the atomic structure of conductive materials, including copper, silver, and gold. Then you will draw the atomic structure of semiconductor materials, including carbon, silicon, and germanium. And finally, you have to draw the atomic structure of some other materials such as gallium, arsenic, and phosphorus. As a solution for this exercise, I have drawn the atomic structure of first 6 materials. The remaining atomic structure can be drawn in the same way. So before going towards the solution, try to do or to draw these atomic structures yourself. The energy bands. As we learned in previous lectures, that valence shell of an atom is also known as energy band or band of energy levels. Means that we can also call the valence shell as valence band. Here, when an electron acquires enough additional energy from external resources, like light or heat energy or from any power or voltage source. This electron will leave the valence band and it will become a free electron. Now these free electrons will exist in conduction band. The difference in energy between the valence band and the conduction band is known as energy gap or simply band gap. Once an electron is in the conduction band, that electron is free to move throughout the material and it is not tied to any atom anymore. To understand the energy levels, we will go through an energy diagrams for insulators, conductors, and semiconductor materials. Remember that in insulators, the energy gap or the band gap can be crossed only when a very high voltage or a very high energy is applied across the material. We will see this in figure 1.7 part A. Similarly, for semiconductor materials, the band gap is smaller as compared to the insulators, and this band gap or energy gap can be crossed if a small amount of voltage is applied as shown in figure 1.7 part B. And finally, in conductors, the conduction band and the valence band are overlapped even under the normal condition or even on room temperature. So there is no gap, or we can say that the energy gap or the band gap in conductors is equal to 0. This thing is shown in figure 1.7 part C. Here in conductors, the electrons move freely from valence band to conduction band. Hence, free electrons are always available in conductors. Here we can see that energy diagrams for all the three types of materials. At first, we can see that valence band and conduction band for insulator has a very large band gap. So if we are in need to enable an electron to leave the valence band and enter into conduction band, we have to apply a very large amount of energy. In part B of this figure, we can see that there is a small energy gap between the valence band and the conduction band as compared to the insulator. This energy diagram is for semiconductor material. While in part C of this figure, we can see that the valence band and the conduction band are overlapped. And this is representing the energy levels for the conductor's material. Here we did not need to apply any sort of energy for electrons to become free. Means that at normal temperature, even at room temperature, or even under the normal conditions, we have free electrons all the time. The comparisons of semiconductor atom to a conductor atom is made in this figure. Here you can see that we have a silicon atom from semiconductor material while we have a copper atom from the conductive materials. We know that the atomic number of silicon is 14. So the nucleus has plus 14 charge in silicon, while the core of silicon atom has a plus 4 of charge. In first shell there are 2 electrons, while in second shell there are 8 electrons. In the third shell of silicon atom there are only 4 electrons. This silicon atom and its valence shell can be termed as a half-filled valence shell. On the other hand, a copper atom is considered as a conductive material. The atomic number of copper is 29. So you can see that the nucleus has plus 29 of charge. In first shell there are 2 electrons, in second shell there are 8, while in third shell there are 18 electrons. In fourth shell of copper atom there is only 1 electron termed as a valence electron. Remember that the core of copper atom has a charge of plus 1. So if we are in need to make this valence electron free electron, we don't need to apply any sort of energy for freeing the valence electron. While on the other hand, in silicon atom, the electrons are tightly bonded to the nucleus as compared to the copper atom. So we are in need of some sort of external energy to turn these valence electron in a free electrons. Now we have to compare two different semiconductor material, that is atom of a silicon and atom of a germanium material. Here are in figure 1.9 the diagrams of the silicon atom and the germanium atom is shown. Again you can see that the atomic number of silicon is 14 and its third shell has 4 electrons, while the atomic number of germanium is plus 32. So the distribution of electrons is such that in first shell we have 2 electrons, in second shell we have 8 electrons, while in third shell we have 18 electrons. So collectively the first 3 shells have 28 of electrons. The fourth shell, which is the valence shell for the germanium atom, has only 4 electrons. So in both silicon and germanium, the valence shell have 4 valence electron. Remember that germanium atom will lose its valence electron more easily than the silicon atom. However, silicon material is widely used as a semiconductor material as compared to the germanium atom, because silicon atom is more stable on high temperatures as compared to the germanium atom. The covalent bond. We know that a bonding of 2 or more atoms by the interaction of their valence electrons is known as a covalent bond. Or simply we can say that when two or more atoms share their valence electrons is known as a covalent bond. Figure 1.10 on next slide represents that each silicon atom is with four adjacent silicon atoms has to form a silicon crystal. Remember that a silicon atom shares an electron with its four neighbors because silicon atom has four valence electrons. So to complete its valence shell, it need to share one electron each with its four neighbors, creating 8 shared valence electrons for each atom of silicon and producing a state of chemical stability. Means that for stable silicon atom, every silicon atom has to share one electron with its four neighbors. Sharing of valence electron produces the covalent bonds that holds the atoms together. The figure 1.11 is representing the covalent bonding in an intrinsic silicon crystal. Remember that an intrinsic silicon material is that material which has no impurity. So the intrinsic crystal will be a crystal with no impurities. Remember that the covalent bonding for germanium atom will be similar as it also has four electrons. So here we will discuss only for silicon atom. Figure 1.1 is representing the covalent bond in silicons. Here you can see that the central silicon atom has four valence electrons while it is sharing one electron with its four neighbors. The bonding diagram is shown in part B of that figure. Here the red negative sign represents the shared valence electron. So we can see that the central silicon atom has now 8 electrons. Similarly, the side or the upper silicon atoms will also share their valence electrons with other neighbors and will complete its 8 valence electrons. Covalent bond in a crystalline structure will be such that you can see that every silicon atom has shared 4 electrons with its neighbors to complete its valence shell with 8 electrons. So the, the tetragonal crystal or the tetragonal shape of the crystal is achieved in a silicon crystal. Thank you very much. That is all for today. If you have any question or any query, feel free to contact at shahid.csit@sood.edu.pk.